All right, moving into Module 8, we're looking at thermal imaging. So this is really its own little beast. Uh, Thermal remote sensing, we tend to use Planck's theory for the most part, which is more of a quantum theory look. And it's also, because we don't deal a lot with reflection in thermal, it's all about emission. So generally speaking, we can see some reflection with thermal remote sensing, but what we're really trying to figure out is how much energy a body is emitting. So it's again a very different beast. It is interpreted a little bit differently, and that's just because the physics are a little bit different as well. So I'm going to start off with some of the physics, just kind of a review of it. I haven't really talked a lot about blackbody radiation and all of the fun components that come with it. But this first objective gets into just some of that very brief introduction of it. So like I mentioned, thermal imaging is really kind of a unique thing on its own, and it has to have a special kind of scanner. So it just detects the wavelengths that come from the object and make that, well, it doesn't make it, but it detects it as a function of temperature. So every type of image, it really comes as some sort of function. So multispectral optical scanners, those are all what they detect the intensity of the energy based on wavelength. When we come to microwaves, it's also like an intensity measure based on either wavelength or polarization or like time of flight. Lasers are all time of flight. Thermal is temperature. So it only falls like within that thermal area on the electromagnetic spectrum. But and so that's the only part that it really looks at. So we're not getting into any of the other radiation, and this is the only one that actually produces heat. So we can operate by day and night with thermal imaging, and which is a huge benefit because at nighttime things still emit heat. Just because we turn off the lights in the room doesn't mean you go cold. so that is an important feature with thermal. When we receive the raw image is actually a black and white image. And it is grayscale, is the other word, right? Thinking back to like module 3. It is a grayscale image, and it's either brightness or darkness. Generally, we use the word brightness. Sometimes you'll see darkness depending on the theory that's being used. But the brightness of the energy is what determines whether it's really high or really low. Now, really high measurements gives me a white pixel because the intensity is high, and therefore it is a hot pixel. If it is black and it's very dark, and that means it has received very little radiation or from the emission, and therefore it becomes a cold pixel. So usually when you guys look at a thermal image that has been prepared, it always has color to it. So we apply a color table usually to a thermal image, or we apply a color slice to an image. So you have blue, like I said, blue is often represented as cool, and red or white is represented as hot. So some of the radiation principles to this, we have a couple types of heat that we have to be aware of. The first one is kinetic heat, and that is how the energy from the atoms pass from one to another through direct contact. So if you were to heat up your hands, rub your hands together for a minute and make them really hot, and then place them down on the desk, you are passing heat from your hands into the desk. And that is considered kinetic heat. So it's actually like not a remote sensing version, but an actual in contact version. Sensible heat is what we can detect from a distance. So that is what the remote sensing sensors are determining. That would be kind of like running a heater and putting your hand in front of it and you can feel the heat coming off of it. That is considered sensible heat. Specific heat is something that we use, a term that is the amount of heat that is required to raise the temperature of an object by 1 degree. So specific heat is, like, for example, if I'm trying to heat up water, how much energy do I need to raise that pot of water up just even 1 degree? And actually for water, it's like crazy high. Like so there's a lot of heat required. Then on the opposite side, we have something called latent heat. And latent heat is the amount of energy required to change the state of an object. So if I want to melt ice, how much energy does it take for me to put into that ice so that it actually melts? There's no increase in temperature with latent heat. It's merely just a change of state. So those are the four types of heat that we have to be aware of. Generally speaking, kinetic heat is like the surface heat, and that's actually what we want to determine, but we use sensible heat in order to detect it, and then we have to calculate what that kinetic heat actually is. So to do this, we have a special kind of theory that we follow, and that is known as blackbody radiation. So the definition of a black body is it's a theoretical or model body, so it doesn't exist, which absorbs all radiation falling on it, and reflecting or transmitting none. So it's a perfect absorber. It is a hypothetical object which is a perfect absorber and a perfect emitter of radiation over all wavelengths. So remember that there is an energy law that states that energy cannot be destroyed, only changed. So a black body absorbs it and then emits it, and it does 100% this with 100% efficiency. This doesn't actually exist in the real world. We try our best to do something like this and try to adjust it. A good example would be the Earthships that you might see, if you've heard about them before. They're buildings that they build out of tires and pounded dirt. And they build that on the north side of the wall, and then they have windows on the south side. And the sunlight comes in, it heats up the tires, and it warms up the house, and then they don't need a heater for it. And yes, these buildings do actually exist in Canada, Saskatchewan, Manitoba, Ontario, BC, of course. There is a couple in Alberta as well. So they exist, they are out there, and they're based on the idea of a black body radiation, because a tire with pounded dirt is a very good absorber, but it's not, and very good emitter, but it's not perfect. So, like I said, we deal more with Planck than we do anybody. And so Planck's law, it examines the spectral energy density of the emission at each wavelength. So you can see there's a formula here, and this is the energy density, as we call it. So don't get too hung up on this formula. I'm not going to, you can see that I don't even give you what each stands for. But the key features that you can see is that it's wavelength dependent. So that's the wavelength. We know it has to do with the speed of light, and it has to do with temperature. So this formula itself breaks down all of that, those components. So those are the parts that are like factors in this. And then of course there's there's constants in this as well. So that's Planck's law. This looks at, it tries to determine that energy density. That's what that formula does. Wien's displacement law, it is the frequency of the peak of emission increases linearly with temperature. So if I increase my temperature, then the frequency that emits the most amount of energy is going to increase. So, and again, you just need to know the definition and in different ways, and being able to describe these in different ways. Stefan Boltzmanns Law it relates the total energy emitted to the absolute temperature. So you can see here that we have the energy and we have the temperature. This is the absolute temperature, and we have a constant that we include in there. So this is a very famous graph that people look at with black body radiation. So as we have hotter temperatures, we have more radiation across the spectrum. So if the temperature was like at 5,500 Kelvin, then we can see that the radiation is much higher than something at 5,000 Kelvin. You can see how it drops kind of exponentially as we go down. And this is all based on wavelength. So we can actually find the optimal wavelength of a black body based on this graph. So we're like, oh, we're going to use this particular wavelength, which would be, let's say, for this peak here, that would be about 750 nanometers. Yeah, 750 nanometers. So that would be, for me at this temperature, that is the temperature that I would want to use in order to collect data. So why is this important? If the Earth's atmosphere heats up, the rest of the wavelengths will increase in their intensity. So that's first one. We need to design sensors that are developed for the heat on the blackbody radiation curve, which is Wien's law. So all of our sensors are all based around Wien's law. So that curve graph, we have to go, okay, so I know that I'm measuring the Earth's surface, and the Earth's surface is this temperature on average. What kind of wavelengths am I actually going to be able to detect, and which ones are going to give me the best results? Then it also gives us, blackbody radiation also gives us a baseline to compare materials. And that's really the most important part, is we have to figure out what the material is in order to be able to identify what the temperature is. Because there's a relationship based on what the material is and the temperature. And that is the Stefan Boltzmanns Law. So we have something called emissivity, and emissivity is a measure of how effective a material is at absorbing and releasing heat. So we have the amount of energy that is radiated, that's what P stands for. A is the area, sigma is the Stefan's constant, and then we have my temperature of the radiator and temperature of the surroundings. So using this formula, I can figure out what my emissivity is. And if I have a perfect emissivity, it would have a value of 1. So generally speaking, or actually pretty much all the time, emissivity is between 0 and 1, unless you have some sort of weird freak of nature. It doesn't go much further than that. So blackbody has a value of 1, and emissivity is anything below that. And the higher the value is, the better absorber and emitter it is. So I'm just going to move into sensor design as well. And so this is sensor design in the different remote sensing platforms, just as an example. And then in the next video, I'll get into the next components. So the sensors themselves have issues that they need to work in. If you guys think back to the atmospheric windows, the thermal energy section has a great amount of areas that they don't have atmospheric windows. So there's a high amount of absorption because of H2O and because of carbon dioxide. So carbon dioxide and water absorb the energy, and then it re-releases it as long-wave radiation, which is thermal energy. So it absorbs the thermal energy, and then it re-releases it as a different wavelength. So the atmosphere causes a great amount of issues for us in terms of like acquiring that information. So we generally have most of the scanners working in the 3 to 5 micrometer range, and after that, everything else kind of gets absorbed, right? There are other spectrums as well, of course, that have little bumps of windows for transmission, but those are more for the multispectral ones, and they tend to be a little bit more noisier. So the scanners themselves are actually called quantum detectors or photon detectors. So if you ever go into a trade show and they tell you that they can see something about you using this quantum detector, it's a thermal sensor. That's all it is. So it's interesting, their interpretation of it, but it's not a fancy scanner. Like, you can buy a thermal scanner that attaches to your phone. Actually, you can buy cell phones with thermal cameras on them, but you can buy an attachment for like $200 now. So these quantum detectors are nothing special other than thermal cameras. So the neat thing about these scanners though is that they're faster than a regular shutter on a camera. The reason they have to be is because really the nature of how noisy the data can be very quickly. So it's a very rapid response. And they also operate on like direct photon interaction. So this is why we have to use quantum physics to do this. So the photons actually interact with the material in the background, and that changes like the electrical charge. If you have too many of these photons getting through because you didn't close it fast enough, then you're going to end up with just a white image. So that's why the scanners have to be so incredibly fast. So the detectors themselves, as you can imagine, can be affected very quickly because if I can detect heat from a distance, like even 6 meters away from a house, which you'd think like standing outside of a house, you're not going to feel heat coming off of it, but you're holding the camera. So what is actually going to end up having a greater impact? Your hands on the camera or the house that's further away at 6 meters? Well, of course, your hands, right? So they have to build these sensors in a way that there's enough insulation on them that they're not going to be affected by you holding on to the camera. So that's a really important aspect of them. And then the present day sensors with that you have up on satellites and up on airborne images, they're all long track scanners, and they have a very high radiometric resolution, more so than any of the optical imagery that we've talked about. And the reason is, again, that because long wave radiation is really lazy, so it doesn't have a very high intensity, especially when you're coming from a distance, right? You think, can you feel the heat from your screen while you're sitting at your computer? Well, if it's a really old one, maybe you can. But even if you think like, okay, the USB port, can you feel the heat from where you're sitting? Probably not. Our skin is not that sensitive. So we really have to have super sensitive features on airborne and satellite to be able to actually receive that. So the downfall with that is that we end up with a lot of noise. So you'll see some of your thermal images when you're looking at them in your Landsat data. You're going to see that there's like kind of stripes in the scanning. And that's just merely the nature of what it is. Like that's how it scanned it, and it's just the noise that it picked up. So there are a lot of different kinds of thermal scanners. Some of them are on other platforms, while other ones are on like airborne platforms. There we go. So here's 3 that are up at the moment. So we have the Tiers scanner, which you guys are working with. It has 2 bands, so that's why we have Tier 1 and Tier 2 with Landsat 8. So the 2 wavelengths fall within the 10.6 and 11.19 micrometers. The spatial resolution is 100 meters, but they resample it down to 30 meters. So now you can understand why when you were looking at the tables and stuff online, it says, oh, the spatial resolution is 100, but it's resampled. Now you know what resampling is. The other one that we have is on Terra, which is the satellite, and it's known as the Advanced Spaceborne Thermal Emission and Reflection Radiometer. And that's ASTER. It was a multispectral thermal scanner. It is. It's got 5 thermal bands between 8.1 and 11.6. So if you're looking to look at like any kind of forest fires or anything about like heat coming off of cities, you're going to use the ASTER data. I actually used ASTER data looking at air pollution down in Mexico City. So that was really kind of neat because we could actually track where the plumes of air pollution were coming from factories. We could actually see it in the satellite. And that one has a spatial resolution of 90 meters. So you can see that these don't have great spatial resolution, and that's just merely because it needs so much energy to be able just to even detect it. The last one is the Moderate Resolution Imaging Spectroradiometer, and that's on MODIS. So this is a satellite, another satellite, and it has thermal emissive bands, which they shorten it as TEB. And so this one has 16 bands, so way more than the other two. But the spatial resolution is now down to 1 kilometer. So again, in space, poor rough spatial resolution, but we have some pretty good multispectral ones up there as well. Then we have ones in the atmosphere. So we have our, whether you put it on an airplane, as a helicopter, or a drone. We have the thermal infrared multispectral scanner, TIMS. It has 6 bands, and it has a spatial resolution of 18 meters. Of course, that's affected by how high you were flying. So that's another one to keep in mind. There are many FLIR systems. FLIR is kind of the top name that you often hear for thermal scanning. Everyone knows FLIR. So you can definitely go to their website and check out all the ones that they've got, because they've got tons of them. I was like, well, I'm not even going to bother giving any examples because I want you to explore that. There's also drone work. So there's MicroTabby, the MicroTabby 640. You put that on a little drone and off you go, and now you've got a airborne thermal scanner that you can use and figure out, maybe how much energy is being released from your rooftop. So that is for the most. Actually, you know what? I can do this one too. I'm changed my mind. I'm doing 8.3 as well. I've got a little bit of time here before the half hour. And at that point, I know I've lost your attention. So I'm going to try to push this as much as I can. All right, so Objective 8.3 is looking at the geometric characteristics of thermal scanners. There is nothing really special about this. So all of these measurements that are on here are just giving you proportions. So don't be like, oh my God, like I have no idea what this is measuring, and does it only stop at 4 meters? And no, depending on the sensor, it can go further, obviously. If you're in space, it's got to go hundreds of kilometers. But this is a similar idea. So we have our whole field of view. So we have a horizontal field of view, which is the x-axis basically. We have the vertical field of view, which is the y-axis. Then we have something called an instantaneous field of view, which is the pixel itself. And then and this is going to be probably collecting the data, and it's showing at 4 meters. So this is probably a terrestrial scanner identifying something at this distance. So the negative of the image is down here, so you can see how it's progressively reducing as it goes. And notice that it is at a straight angle. Using thermal imaging, you have to have it straight on. Otherwise, you may end up with some sort of bias at different angles. It is difficult to do, especially when you're dealing with a house and you're trying to get images from a house at like ground level. You should have if you're going to go into thermography, you should have a ladder that gets you up to where you need to go, and then you can do a straight on image, because that's going to give you the best options. Otherwise, as you change your angle, you're definitely going to see a difference. So that's the basics of the geometry. The calibration is a little bit different because it does still kind of go with the geometry, so I'm going to include this here as well. And this is, there's 2 different kinds of calibration. And the first one is known as internal body source referencing. And the reason I bring this up like immediately after the geometry is because there's still some geometry in this that needs to be taken into account. So I just finished talking about the instantaneous field of view and the horizontal and vertical field of view. So if I have my infrared telescope at the top here and some sort of filter, because there always is a filter, I have a long track scanner, and it's kind of rocking back and forth in this case. The reason it's rocking back and forth is because I'm scanning from one side to the other, scanning one side to the other. This would be still a cross track, but it's just collecting information one bit at a time. So now we have 2 different types of black bodies that are in here. And so we have what we call the reference black body, and then we have a test black body. This is the hot and this is the cold. So the calibration of this, when we're using this rocking mirror, it says, oh, this one should be white, this one should be black. And it keeps it within that range. So this is always going to be my white pixel. This is always going to be my black pixel. If it exceeds that temperature, it's going to be white or it's going to be black. That's all that happens. So this is all happening within the actual sensor itself. And it is calibrating within itself. So every time you turn on that camera, every time you scan with that camera, it applies this. So this also helps with managing the heat around it from your own sources, right? When you're holding the camera, or perhaps you have a heated airplane versus the exterior. This is what's helping manage that. Then we also have the empirical referencing, external empirical referencing. And this is based on actual data collection on the ground. So this is where fieldwork comes in. This is really the most precise way of being able to calibrate your thermal imaging so that it actually is at the right temperature. So you would collect atmospheric information at each layer of the atmosphere. We do this through lasers. It's actually a very expensive piece of equipment, but very accurate. Then you model that atmosphere over all those layers over the area. And you're going to have a hot value and a cold value within the area that you are working in. And you're going to know what those values are. So you're like, this is exactly what the temperature is on the ground. And there's fancy math. Again, I don't care that you know that. I just need you to know what these are. And then you can apply an equation that to change that radiation to so that you know what is 0 and what is 255 or what is hot. So that's the second kind of calibration. Both of these are based on using that field of view. So and then looking at the instantaneous field of view. So the instantaneous field of view will be adjusted based on what these calibration results come up with. So that kind of summarizes all of the theory. Objective 8.5 still has some more theory in it, but I will introduce that in the next lecture or in the next video. And then I'll also be talking about the applications of it.